made this presentation file and composing how to explain it effectively. And also, ran PHDL simulation, collecting information about recent works of adiabatic circuits, and I, in Yongmo, am doing this presentation. We've done some research to find what is the most effective among some adiabatic circuits, and we considered LPAL, developed from PAL, solving its energy loss problem, the one that fits. I'll describe what the adiabatic circuits are, and then show you how LPAL works, and then the results of simulation, conclusion, and references now. Here in the world of integrated circuits, say CPU, we used to increase its frequency to advance its speed. We actually know it from Moore's law, and its technological trend had been all concentrated on its speed, not energy effectiveness. However, we found out its energy use was increasing too as the speed goes up. And as the energy loss is going up, we also have been needed to find out how to cool it and how not to waste it. Here's some problem occurred. And we were convinced to develop some methods to solve this problem. The technology trend recently was going into decreasing its energy use and loss. And to solve this, we should know how the energy is spent. As you can see here, the energy loss could be divided into three parts. One is dynamic energy, and the second is for short circuit, which occurs when PMOS and PMOS will turn on. And the last one is the leakage power. Among these, the dynamic power takes 70% of whole energy use. So many people would rather find out how to decrease the dynamic power. Static CMOS energies come from the load capacitance and the source power that we couldn't control. However, in the adiabatic circuits, they were totally under control due to the added part of RCL of T. With this term, we could lose energy use and vice versa. Then, what is the difference between these two? At first, the waveform itself is different. Traditionally, in a way of static CMOS, we can see the input voltage surges while the input voltage increases gradually in adiabatic circuits. And with this method, we can charge some leftover energy to load capacitance and use it from it. Secondly, its optimum operating frequency is seemingly low for adiabatic circuits. Third, if the charging time were more than 2 times of RCL, then the energy effectiveness is much greater than it from static CMOS. Fourth, adiabatic circuits are energy recovery circuits, while static CMOS is not. So far, I wanted to make sure that the adiabatic circuits are greater than static CMOS. There are many kinds of adiabatic circuits, such as ALD, 2N2P, PAL, CPEARL, SCAL, TSCL. And you can see here, we could distinctly mention that PAL is greatly effective than some energy loss ones. PAL is also good for replacing and applying to the original systems, which is made for CMOS logic. The only thing we should do is to replace the adiabatic circuit to the CMOS part. However, PAL has some problems. PAL uses energy using clock, whether the system is on or not. To solve this, LPAL was made. LPAL is totally similar to PAL, except for the control component. The control component plays a role letting the source stop using energy. When the mode is 0, the upper part is on, while the below part is off. Since here in the upper part, slash mode is 1 and it goes to NMOS MP3, which would be 0 for its input is 1. By the same logic, we don't have to use power when the system is off, and also we can solve clock skew problem. Here's the VHDL code for PAL inverter and its test bench. And the code for LPAL is here in the next page. The difference you can see here is the existence of the variable named mode. As you know, when mode is 0, the circuit does not work since we put U into the output, which means uncountable. We also decided to have VPC clock period 10 milliseconds and input changes in every 6 clocks. That means the one cycle of the input should be 120 milliseconds. Only at rising edge VPC changes, and when its input is 0, output would be turned into 1 from 0, and vice versa. Here's the result of the simulation. Despite the delay of the output for the first 120 milliseconds, it works anyway. Things you could find here is that the output would be 1, when its input is 0 at its rising edge, and the output would be 0 when its input is 1 at rising edge. On our next page, you can see the circuit doesn't work when the mode is 0, as you can see here. But when its value is 1, then the circuit would work out as if it were a PAL circuit. For a certain amount of time, if a circuit works only 70% of the whole time, then it would waste almost 30% of energy. But we could save 30% of energy with LPAL circuit since it doesn't have to work for 30% of time when mode is off. I mentioned why adiabatic circuits are better than static CMOS and chose LPAL for its energy effectiveness. For most cases, and statistically, LPAL is 44% energy effective than PAL, which is also an adiabatic circuit. So I don't think I have to tell you how great LPAL is and the lower circuits. Here's the differences. Any questions?